Over the last century, engineers have tried dozens of ways to keep the wheels planted. Today, we are breaking down 10 distinct suspension architectures to understand the engineering compromises under your chassis. We start with the leaf spring. This is the foundation of automotive suspension, and its design actually predates the car by hundreds of years. If you look under a modern pickup truck or an old classic car, you'll see them. A leaf spring is made of several strips of curved steel called leaves stacked on top of each other. The longest leaf is attached to the car's frame at both ends, and the axle sits right in the middle. When the truck hits a bump, the steel leaves flatten out to absorb the energy. Because the leaves are layered, they rub against each other, which actually helps provide a little bit of natural damping. The big advantage here is strength. Leaf springs can spread heavy loads over a large area of the vehicle's frame, making them perfect for hauling heavy weight. They are also simple and cheap to build. However, they are heavy and don't allow the wheels to move independently. If the left wheel hits a bump, the right wheel feels it too. This leads to a bouncy, truck-like ride that isn't very precise. You'll find them in most heavy-duty pickup trucks, like the Ford F-Series or Chevrolet Silverado, and almost every American car from the early 20th century. As cars got faster, engineers wanted to move away from solid axles and let the wheels move on their own. This led to the swing axle. Imagine the rear axle is cut in half. Each half is attached to the middle of the car with a hinge. The wheel is fixed to the outer end of that half shaft. This allows the left and right wheels to move up and down without affecting each other. It was a huge step forward for comfort on rough roads because the whole car didn't tilt every time one tire hit a rock. It's a very simple way to get independent suspension, but it has a major safety flaw. Because the wheels move in an arc, the angle of the tire changes as the suspension moves. In a hard corner, the outside wheel can actually tuck under the car. This makes the back of the car pop up and can cause the driver to lose control instantly. You'll find it in the original Volkswagen Beetle early Porsches, like the 356 and the Chevrolet Corvair. To fix the weird angles of the swing axle, engineers moved to the trailing arm. This is a very common setup for the rear wheels of smaller cars. Think of a trailing arm like a hinge on a door. One end is attached to the chassis, and the arm points toward the back of the car. The wheel is attached to the other end of that arm. As the car moves over bumps, the arm simply swings up and down. Because the arm is parallel to the car, the wheel stays perfectly straight and doesn't tilt inward or outward. The biggest advantage is space. Because the arms are tucked away, you can have a much larger trunk and more room for passengers. It's also very predictable for daily driving. The downside is that these arms don't handle side-to-side forces very well. In a sharp turn, the arms can flex, which makes the steering feel vague or squishy. You'll find it in many classic French hatchbacks and the rear of many front-wheel drive cars from the 90s. The semi-trailing arm is the middle ground between the swing axle and the pure trailing arm. It was the sporty choice for decades. It looks like a trailing arm, but the hinge is mounted at an angle, usually about 15 to 25 degrees. Because of that angle, the wheel doesn't just move up and down, it also tilts slightly as it moves. This tilt is actually helpful because it helps the tire stay flatter against the road when the car leans over in a corner. It offers much better handling than a standard trailing arm and takes up less space than more complex systems. However, it's famous for lift-off oversteer. If you let off the gas or hit the brakes while turning hard, the geometry shifts suddenly and the back of the car might try to slide out. You'll find it in legendary drivers' cars like the BMW E30 M3, the Mercedes-Benz 190E, and the Datsun 510. While European companies were focused on handling, Ford was focused on making a two-wheel drive truck that could survive a construction site. They came up with the twin I-beam. This uses two long, solid steel beams for the front suspension. The beam for the left wheel is attached to the right side of the frame, and the beam for the right wheel is attached to the left side. They literally cross each other under the engine. This gives the truck the strength of a solid axle, but allows the wheels to move independently. It's designed to take a massive beating without braking. It is arguably the toughest front suspension ever put in a light truck. It's simple and requires very little maintenance. The disadvantage is that as the beams move up and down, the tires tilt significantly. This causes the tires to wear out unevenly and makes the steering feel a bit disconnected, especially on the highway. You'll find it in the Ford F-150 and Ranger trucks. Sometimes you want to keep a solid axle, like on an off-road vehicle, but you need more control than leaf springs can provide. That's where the 3-link comes in. It uses 3 metal rods or links to hold the axle in place. 2 links run forward to stop the axle from moving front to back. The 3rd link is usually on top of the axle to stop it from twisting when you accelerate. To stop the axle from sliding out the side of the car, a 4th bar called a panhard bar is added. By using rods with rubber bushings instead of a stack of leaves, the axle can tilt much further. It's incredible for off-roading because it lets the tires stay on the ground even over huge rocks. It also handles power better than leaf springs. The downside is the panhard bar. Because it's a solid rod that pivots, it actually pulls the axle slightly to one side as it moves up, which can make the car feel like it's wiggling over bumps. You'll find it in the Jeep Wrangler and many dedicated rock crawling rigs. The 4-link is the evolution of the 3-link, designed for maximum control and stability, especially in high-performance vehicles. It uses 4 main rods to hold the axle. There are 2 different ways to set this up. In a parallel setup, the rods all point forward. In a triangulated setup, the top 2 rods are angled inward to form a triangle. The 4 rods hold the axle perfectly centered. If they are triangulated, you don't even need a panhard bar because the angle of the rods stops the axle from moving sideways. This is the best way to locate a solid axle. It provides amazing traction for drag racing and a very stable feel on the street. However, it's much harder to package under a car because you need space for 4 different mounting points on the frame. It's also more expensive to manufacture than a 3-link or leaf springs. You'll find it in high-end drag cars, many modern Ram trucks, and classic muscle car restorations. If you look at a Formula 1 car or a high-end sports car, you will almost always see double wishbone suspension. It is widely considered the best design for pure handling. It uses 2 V-shaped or A-shaped arms, one on top and one on the bottom. These look like wishbones, which is where the name comes from. The wheel is held between the points of these 2 arms. Because there are 2 arms, engineers can make the top one a different length than the bottom one. This allows them to control exactly how the tire touches the road. When the car turns and leans, the wishbones pull the top of the tire inward. This keeps the tire perfectly flat against the ground for maximum grip. The advantage is perfect handling and a lower hood line, since the suspension stays low to the ground. The disadvantage is that it's very complex, takes up a lot of horizontal space, and is expensive to build because it requires so many parts. You'll find it in the Mazda Miata, older Honda Civic, and almost every supercar from Ferrari to McLaren. If the double wishbone is the high-end choice, the McPherson strut is the choice for the rest of us. It is the most common front suspension in the world today. It simplifies everything. It uses 1 lower control arm and 1 tall vertical post called a strut. The strut contains the shock absorber and the spring, and it also acts as the top pivot point for the steering. It's a space-saving miracle. By getting rid of the upper wishbone, there is plenty of room for an engine and a transmission in a small front-wheel drive car. It's incredibly cheap, lightweight, and easy to maintain. It works perfectly well for 95% of drivers. However, it isn't quite as good for racing. Because the strut is so tall, the tire doesn't stay quite as flat during hard cornering as it would with double wishbones. It also requires the car to have high towers in the engine bay to hold the top of the struts. You'll find it in just about every modern sedan and hatchback, from the Toyota Camry to the Porsche 911. Finally, we have the most advanced system of all, the multi-link. This is where engineers stop using simple shapes and start using high-level math. Instead of wishbones or struts, a multi-link system uses a series of independent rods, usually 4 or 5 per wheel, all pointing in different directions. Each rod has a specific job. One might control the wheel's angle during braking, while another handles cornering forces. Because they are all separate, engineers can tune the suspension to be extremely comfortable when you're cruising, but very stiff and responsive when you're driving fast. It is the ultimate compromise. You get the ride of a luxury car and the handling of a sports car. The downside is obvious. It is incredibly expensive, very heavy, and very complicated. If one of the many rubber bushings wears out, it can be difficult to find which one is causing the problem. You'll find it in the rear suspension of most modern luxury cars like Audi, Mercedes-Benz, and high-end SUVs. Suspension is never a finished science. It's always a trade-off between cost, space, comfort, and grip. Whether it's the simple steel leaves of a truck or the complex multi-link setup of a luxury sedan, Every arm and bolt has been calculated to keep you safe and comfortable. Next time you hit a bump, remember the engineering happening just inches below you. If you found this breakdown helpful, let me know which of these systems you'd want under your next car.